Welcome back, everybody. So now we are going to move again to a part that might be easier, more practical, about creating views and indices. I'm not going to be done today. We'll continue and finish next week. So let's start with a bit of a rehearsal. So we have a sample table right here. That is a table of publication by various famous people. So we have the author of the publication, varchar 30, which is a string limited to 30 characters. Then we have title, varchar 255, and year is an int, that's the year of publication, all right? So this is a table, it's called publications, and we are going to run a few SQL queries against it. So that should not be new to you, it's all things that you've seen. For example, this query right here, select star from publications where author equals Albert Einstein. What kind of query is that in the relational algebra? Let's see, selection, right? Just selecting some of the rows where we have Albert Einstein, right? Sorry. So now let's look at that one. This is also a selection, but it's different. It's Mariam Mirzakhani. And I might also do this. What is it called? Projection, right? That's a projection on title and year. Now we have this entire table. And here we have both a projection plus a selection right here that, now has both less columns and less rows. Okay. Now we have grouping queries with group by. So here I group by author, and for every author, I get the count of the titles, right? How many titles there were. I could also have written count star in that case. Note that I did it nicely in the sense that I have exactly my grouping key. So there's only one author that is also in the select clause, and I aggregate only for the other keys, in that case, title, right? So I did it correctly. It's easy to get it wrong with the group by, right? To basically not have the same, for example, to have only some of the grouping keys in the select clause, that would be bad, or to aggregate grouping keys, that would be bad too, or to forget aggregating non-grouping keys, right? But this one is clean, and we get this with the three distinct authors on which we grouped, plus the number of publications, which is 7, 2, and 2. Okay, I also use the rename with as, right? I can also order things. For example, I can order by year, which by default is ascending, and I can even paginate with limit and offset, meaning that I jump over the first two and that I take the next three, right? So this would be giving me that. All right, for whom is that clear? You've all seen that, right? Now you're the masters of SQL, so you know exactly how to write these queries. You can even combine, right? You can have select from where, group by, having, order by, limit, offset, right? All of that in that order, always in that order. Okay, now here are 4 queries. What do you observe in these queries? Does anything catch your attention? Nobody sees something? Yes, go ahead. It's the same, exactly. It's the same query. You see this select star from publication where author Albert Einstein is always the same one, repeated. Yeah. That is kind of, well, it's not inefficient for the execution, but it's inefficient for you that you wrote every time the same thing all over again. We would like to shorten that, right? Is there a way that we can just give it a name and just reuse the name? So in that case, this is the query at hand. And what we can do is give it a name, right? So I could call it, for example, publications by Einstein. I save it under that name. Then I could reuse it, right? And the way I can do this is something you can do with PostgreSQL. You can say create view publications by Einstein, just like create table, but here it's create view as, and then your select star from where queries, right? Query. And then what you can do is then use it whenever you need it. You can just use as if it were a table, like this, right? So you can take the shortcuts. For whom is that clear? Right? That's called a view. So you can basically store the results of some query, give it a name, and you get a view. And that you do with the create view statement. Now you can query views as if these were tables like this. So it's you don't really see the difference with a table. You can create different column names. For example, in that case, we would have title and year, but what if I want to give them different name like T and Y? I can also do that. I just then add my names after the name of the view, right? And that brings us to the fact that now we don't have only two types of relations, those that have a name and those that don't have a name, but now we have three. We basically have the persisted relational tables, those we define with create table, yes? Oh, with would be only for a specific query. Create view is permanent, like you create the view and then you can use it all you want with a name. With would not give a name that would stay, right? After you're done with the query containing with, that's forgotten again. Right, that's the difference. A view is really stays with its name, right? So we have the relational tables that are persisted. They are stored on disk. There are the relations on the fly. These are the ones that pop up in your Jupyter notebook below your query. But as soon as you close the notebook, it's at least it will stay if you save the notebook. But I mean, PostgreSQL will not remember it, so it's on the fly. And now we have third kind, that's called a view, that is also named. So it's named just like a persisted table, but it's recreated on the fly whenever you need it. So it's not like it's stored. So the idea is that a table is named and persisted. A view by default is named but is not persisted. And on the fly is neither named nor persisted. Now, what does it mean that the view is not persisted by default? It means that if I have the query now, I come back to that query right here. It's going to take a bit more time to execute it because publications by Einstein, if it were a relational table, you just read it from disk, right? But publications by Einstein is a view. It's not a table. It means that you cannot just read it, that you cannot do. You have to recompute it. So it's as if you were replacing that. You were replacing it with this, right? So for this reason, it might take a bit more time. For whom is that clear? Right? Just because you did not persist it. So it's only a shortcut. It can also be called a syntactic sugar if you want. And so it might take a bit more time. However, there is a way to ask nicely PostgreSQL to persist a view. That's called the materialized view. And you have instructions, I don't have them on my slide, but you have a way of, say, create materialized view of this and that. Now, you need to understand something with materialized views. It's that when you do that, create materialized view, it's going to execute the query and store on disk a copy of that table. But what if the data in the original table, so that would be in the table publications, if the table publications is modified and you materialized that view, then you will not see the modifications because they happened later, right? So you need to be careful if you materialize your view that it takes a snapshot at a certain moment in time, and then you will not see anything that changes. You would have to refresh the materialization. For whom does that make sense? Right? It's like taking a photography. The photography is a snapshot, and then people might go ahead and do other things, but the photography is still stuck at the moments that you took it, right? So a materialized view is really a photography that you take of the query and you store it. Okay, but if you don't say anything, then it's not going to be persisted. Okay. Now, let's move on to something slightly more complicated, but not too complicated, I hope, is what happens if you update a view. Updating a table, you know what that does, right? You can delete a row, you can modify the value, some value corresponding to some record and attributes. You can insert a new row and so on. So that on a table is not a problem, the persisted table. What if you do that on a view? Because a view was already created for something from something else, right? How can you modify a view? Well, it doesn't make sense in the sense that the view has to be what the query tells you. But what if we could make it make sense to modify a view? If you think like a mathematician, what would have to happen? Well, as the user, what does it mean that I update a view? It would mean that, for example, I query the view with select star from the view and I see the content. Then I write an update or insert or delete query on the view. And then I again do select star from the view. I should see the results of my change, right? So then I could have said, I have updated the view, or it's as if I had updated the view. Now, for this to happen, you should not forget that since the view is derived from original data, you would have to modify the original data in order to get that change. So that gives us a mathematical problem. If I want the view to be updated in this and that way, then in what way should I update the original data in order to make it happen using the derivation of the view from the table? For example, imagine that I have this query. I want to modify the view. That's a view, right? It's not a table, it's a view, publications by Einstein. So I want to insert into that view Albert Einstein foo 1920, right? So what I would like to see is a new record, right? This is what I would like to see if that happens. But don't forget it's a view. So how could I modify the original publications table in order to make that happen? What would I need to do in the publications table in order to make that new record appear? So what should I modify in the table publication? So that's the table. Publication is this table here. What should I modify in that table, publications table, in such a way that when I create the view out of it, I would now get this? What should I modify in the original table? Anybody? Well, this, I could just add these three values, Albert Einstein foo 1920, in the original table. I could add it to publications like this. And then when I create the view, I get this. For whom does that make sense? Right? Because the view is created by filtering on Albert Einstein. So if I add this to the table and I filter by Albert Einstein, then I get this and I see my updates. So there was a first question over here. Go ahead. Yep. I will read. Yeah. That is very good thinking. I will repeat it for those on Zoom. What you said, this is very good thinking. That's exactly the direction in which I want you to think. So for those on Zoom and from the future, the question is, what happens if the view would not have exactly the same columns as the original table, but would have, for example, less, just title or year. And then we want to update the view by adding author and title, but then we don't know what to add for the year, right? That was your question. And in fact, I have slides about that, but I can already tell it now. you could make it work if year had a default value, or if it would be allowed to be null. And then that's exactly what you say. You would exactly do that. You would basically add a record to the original table with the values for the columns you have, and the rest, you use the default value, or null if there is no default value. And imagine that there is no default value for the other columns, and there is also not null in the constraints. Then that's an error. Then you cannot do anything to the original table to make it such that that would be the view. Well, you could, but you have to make up value, and that's you don't want to do. Does it answer your question? Yes, go ahead. No, that we don't do. So the question is it possible to modify the view without modifying the original data? No, we don't. The reason we don't is the view is really tied to the original data, because this here, the query we have, that must stay that way. It has to be, that is the link between the view and the original table. And this we don't want to break. We really, really want to maintain that. So whenever you want to modify the view, the only way you can do that is by modifying the underlying data in such a way that you cause the view to change in the way the update goes, right? We had another question. Yeah, go ahead. Yes? Mm-hmm. So let me repeat your question, then you can tell me if I did a good job of that. The question is a practical question. In practice, do I need, as a SQL user, to create a query against the original table, or can I actually write a real update or insert or delete query against the view? And the answer is the latter. You can and should update the view we using this. I think I think this is what I wrote here. Yeah. So here I say insert into on the view, and that works. You can really do that. So basically, the part where this is modified is automatic. This is done by PostgreSQL, and PostgreSQL will take care of modifying the underlying table for you, right? So that's very convenient. It's really a convenience that the system gives you, right? Did it answer your question? Awesome. Go ahead. Yes, if it's not materialized. If the view is not materialized, then it will automatically propagate. Materialize means you take... Yeah, because it's not materialized. Yeah. Mm-hmm. Yeah, then you see it. Yeah. Yeah, I'm going to repeat also for those on Zoom. So the idea is really that if instead of having an update against the view, you have an update against the original table, and then you try to look at the view, then you will see the changes, right? You will see the changes. There is an exception to that. That is the notion of materialized view. That's basically what I told you earlier, that in some cases, you can take a picture, like literally with a camera, you take a picture of the table. I could actually literally do that, right? I could take a picture and then put it somewhere, and then I update the table. Of course, the picture is not going to change, right? This is called the materialized view. A materialized view is going to be faster, because in that case, you don't need to actually recompute it, but it's going to have staleness, in the sense that when you update the underlying table, you will not see the changes, except if you refresh, if you take a new photo or a new snapshot, right? But on my slides, for now, I'm assuming a non-materialized view, a normal view, that the default is that it's not materialized, right? I just told you can, if you want, materialize the view. Does it make sense? Yeah, okay. Any other questions? No? All right. Okay. So technically, we can do insertions, deletions, updates, treat it just like a table. If it doesn't work, you're just going to get an error. If PostgreSQL is not able to modify the underlying data to make that update work, right? So the sort of more complex things that you could want to do, you know, you can try to push PostgreSQL to its limit. It's a bit risky because if you push it too far, you're just going to get errors, because that might be too complicated to figure out how to modify the underlying data. For example, if you have this view that is obtained from joining tables by year and so on, and you try to update it, you need to see that you're pushing PostgreSQL to its limits by doing that. If you try to update that, because in that case, you would need to you would need to update two tables to make the view updated. And in that case, if you want to push it, we're back to your question. If you would like to modify that view, in that case, it's a select star. So technically, you could add records in both tables that are obtained from the projection of the new record, the new record you want to add. So that might still work. As soon as you replace the star with some columns, then that might start breaking if you don't have default values or nulls to populate it with, right? All right, and you might think about it, but again, by adding, imagine that, just to make you think, imagine that I want to update the view by adding a record. What might happen is that I'm creating phantom records in the view. Because imagine that I have, in my view, I already have a record with the year 1905 that has maybe Einstein with it on the publication side. And the other table, it has, let's call it alpha, right? Einstein, 1905, alpha. It means that in my original table publications, I had Albert Einstein, 1905. And in the other table, I had 1905 alpha, right? Now, what if I try to add a new record called Mirzakhani 1905 beta in my view? It means I would have to insert Mirzakhani 1905 in the first table and 1905 beta in the second table. Do you see what's going to happen now if I recompute the view? I'm going to get two phantom records. I'm going to get Albert Einstein 1905 beta and Mirzakhani 1905 alpha. In fact, that's very similar in spirit to what we saw with the Chase algorithm and the decomposition of the Boyce normal form, right? So you need to be careful. This is absolutely not trivial. And again, you're likely to get an error as soon as you try to update a view like that, right? The easy case to update a view is views that look like that are just some selection, some very simple view. Otherwise, it gets too hard. So this one is not available, is not updatable for that reason, that you could create phantom records if you have multiple times the same value on the joining key. All right. That one is also not updatable because we don't have the default values in there. Yes? Yes, in that case, it's a join. In that case, it's a view that is the join of two tables. Yeah, absolutely. Basically, when I have from with a comma, the comma is only a shortcut for the Cartesian product, right? And it's a join because of the Cartesian product plus the where clause. That has the year equals other table y. All right. Now, there are a few simple rules that guarantee that it's updatable. The first constraint that guarantees that to you is only one table in the from clause. No joins, no fancy things, just one single table. The second constraint is if you have all of the attributes in the select clause or select star, then you don't run into the issue that you said earlier that you might not know what to put in the attributes that are not in the view, except if they have null or default value, because then you can take that when you insert a new record. And the other constraint is that you cannot use the relation itself in the where clause. This has to do with the fact when you nest queries in queries in queries, you can actually do complex things Like, for example, you can have the original table, select blah, blah, blah from the original table, where some value equals, and then again, select blah, blah, blah from the original table and so on. That just makes it too complex to propagate the update. So that also would break things. So what these rules are telling you is really just keep it simple. If you want your view to be updatable, then don't push it too much. Just stick to something simple like select star from where, and the where should not be too fancy. It should just be a simple like equality, comparison, something like that. But no nested things. Okay. All right. Does it make sense? Of course, it's a guarantee, right? But you might in the future have people who manage to find ways of propagating updates in more cases than that. But at least for now, these are kind of the current rules. And it might also differ from product to product. Maybe if you use IBM or Oracle, maybe they have different rules. Okay. Any questions so far on the views? Yes, go ahead. The R itself. So I meant the original table, the one that you have in the from clause. You cannot also have it in the where clause. The way it could happen is if you have a query in a query in a query in a query. You might have queries that look like select star from publications, where year equals, and then you have some nested complex query that again uses a select from publication. Maybe you compute the maximum year or whatever, like for an argmax. And that is forbidden here. That's what the third one means. You cannot have a too complex where clause with nested queries in there, right? Any other questions? I'm basically done with the views. So if anything is unclear. Okay, who feels like you could create views now in SQL? Right? Create view, blah, 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 as, and so on. Who feels like you could try to update views? Okay. Okay, you can try. Just try it in PostgreSQL. Create data, create a view, try to update it, and see what happens. And try to create a view that is not updatable, and try to update it. Right, just as a small practical exercise. All right. Very good. Now we have a few more minutes. I'm going to switch over to something kind of related, but not directly, which are indices. Indices are extremely powerful. They make your database faster. They make your database system faster. Have you not wondered how you can go to a website that has millions of products and you type some search in the bar and click return or click on the search button, and in less than 1 second you see the products? How can it be? It's millions of them, right? How can it be so fast? And the answer is indices. And now I'm going to show you the secret of that. How can it be that these websites are so fast giving you the information you're looking for? But I would like to say something first. Who remembers reading a book, and at the end of the book, in the last pages, there's maybe, let's say, 10 pages with an alphabetical list of words, and after each word, there is the pages on which it appears. Who has already seen that? This is an index. Okay, I'm done, I can go. Right? This is an index. This is exactly what it is, and we just do the same thing for relational tables. So an index is an additional structure. It's outside of the book, right? It's not the actual text of the book. It's extra pages that you add at the end that allow you to very quickly look up where to find some information in the book with the pages. So let's build that for relational database systems then. So we have this query, select star from publications where author equals Albert Einstein. So this is my whole table. Now, if I want to execute that query, now think of how I would execute that query. It's a selection, right? It's a selection. So I have to go through the rows. And for every row, is it or is it not Albert Einstein? If it is Albert Einstein, I keep it. If it's not Albert Einstein, I don't keep it, right? But I need to go through the rows. That's called a full scan. It means that I really go row by row on the entire table, and that takes a while. Now That's what it, oh, yeah, I had an animation, so I can show you the animation. Okay, so we do it. Where author equals Albert Einstein. First row, yes, we keep. Second row, we keep. Third row, we don't. Fourth row, we keep. Here, we don't. We keep, we don't, keep, we don't, and we keep. That's how I execute a selection, right? For whom does that make sense? Right? Full scan, row by row. Now, as you might imagine, when you go to Amazon to order something, it's not going to scan row by row if this is the iPhone you're looking for. Right? So this is not how it works. And then we get that. Some queries, here it's another one, are highly selective. This one is not very highly selective because Einstein wrote so many papers that I'm going to get a lot of records in the output, right? What about a highly selective query? This one is very specific. It's looking for a very specific article called the theory of relativity. And again, let me try with the full scan. Is that the theory of relativity? No, that's not the theory of relativity. Is it the one? No, also not. Maybe this one? No, also not. Maybe this one? No, that's also not the theory of relativity. Maybe this one then? No, also not. Maybe the next one? Also not. Maybe the next one, that's also not the theory of relativity. Maybe this one, also not. Maybe this one, no. Maybe this one, no. Maybe this one, yes, this is the one. I was unlucky, it was the last one. It doesn't have to be the last one, but in that case it was. But you see that it was slow, right? Could you imagine if this was happening whenever you search on Google or you try to find something on the internet, you could come back in a year for the, scanning the whole table looking for what you're looking for. So obviously there has to be better ways. So that's our result. Can we do better than that? Of course we do, because otherwise I wouldn't have a whole lecture of indices. So yes, we can do better than that. I'm going to help you a bit. This is the same table, but I just put the tuples in a different order. Now, if I look for mathematical logic, how fast can you find it? Who sees it? Mathematical logic? Yeah. How fast were you? Did you need to scan through, or did you find the trick to not have to scan through? You scan through? Okay. Does anybody else have a way? Yes? Yes. That is true, yes. Exactly. So you're making an excellent point. So yes, you basically notice that it's sorted alphabetically. You're also making a good point that in order to find out that it's sorted alphabetically, you needed to do a full scan. But imagine that now I tell you it's sorted alphabetically. I'm giving you a list, it's sorted alphabetically. What's the complexity with which you are going to be able to find the records? Does anybody of you have a notion of complexity theory, algorithmic complexity? Some of you. What do you think it is to find if it's alphabetically sorted? You're not computer scientists, right? So I don't actually expect that you would know that sort of things. Yes? Log of n, exactly. That's exactly the right answer. Who understands log of n? Why log of n? Many of you probably don't, right? So yes, congratulations. That's exactly the answer. I'm going to try to give you an intuition of what that means. The first thing it means, it's better than the full scan, right? The full scan, we call it O of n. What it means is that if you have n records, that's the size of your database, the number of records, then the time it takes to scan through the database is proportional to n, right? It's n and a constant factor. It means in particular that if I double the size of my table, then the full scan will take twice as much time. If I have 10 times the size of the table, then the scan is going to take 10 times as much time, right? This is called linear complexity, right? It's proportional to the size of the table. Now, the reason why it's more efficient with the alphabetical order, and I will explain then why it's logarithmic, the reason it's more efficient is that you've learned in primary school how to look up a word in a dictionary, right? If I give you a dictionary and I ask you to look for Huhirashli, then you can just look it up with binary search, right? You open randomly, is it before K or after K, and then you just go, it's called a binary search. You always cut it in two, all the way until you arrive to your page. And you probably noticed that looking up that word in the dictionary is much faster than reading through the entire dictionary, right? I don't think anybody did. I tried to read through the dictionary, then I stopped. So I know all the words that start with A and AB and so on, and then I stopped, right? So you cannot read the whole dictionary. The reason you can look up a word easily is because you use the fact that it's alphabetically sorted, and you just use that binary search. Now, the intuition behind logarithmic is that if the size of my table is n, then the time it will take me to do that, the binary search, looking for the alphabetically sorted records, is going to be proportional to the logarithm of n. Just as a rule of thumb, imagine I have a table with 100 records. Let's say it takes me 1 second to query it. Now, if I have 10 times as many records, it would take me 10 times as much time for a full scan. But if I use a binary search, if I have 10 times as many records, maybe it's just going to add half a second. So going from 10 to 100 just goes from 1 to 1.5 seconds. If I again multiply it by 10, I go from 1,000 to 10,000. Then I again only add half a second. So the effect of going from 10 to 100 is the same effect as going from 100 to 1,000, is the same effect as going from 1,000 to 10,000. It adds a constant amount of time. That's the power of logarithm, right? Who gets that, roughly? Let me show you as an animation here. Why was it so fast? Because you pick somewhere in the middle, that's the binary search. It doesn't match, yes, but we also know that O is after M. So I can already forget about that and focus on that part. Then again, D comes before M. So I forget about this and come there. And you see, the reason why it was fast is, let me rewind. How many comparisons did I make here? 1, 2, 3, and 4. I only made 4 comparisons. If I had had a full scan, how many comparisons would I have had to make? As many as records. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the full scan would have needed 12 comparisons. But here I was able to only use 4. So logarithmic is much, 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 much better, right? So it's really this intuition that every time you multiply the size of your table by 10, you add a constant amount of time. Half a second, okay, for example. All right, you can actually visualize it. I mean, all the possibilities when you compare like this, you could actually see it a bit like a tree, like this, where I organize now my records like this, where that's the one I compared when I started, right? And imagine that everything that's above it, above this, I put on the left, and everything that's below it, I put on the right, which is what I did here, right? Everything on the left that was before, everything on the right was after. Then I cut the drone from the phenomena of capillarity that was this one here, right? So again, I cut it in two, goes to the left of the left and then to the right of the left, right? And then this is how I can basically build that. So now if I reason with that structure on what I've been doing when I compared, is that I picked the one in the middle. O is after M that I'm looking for. Then I go on the left. D is before M, so I need to go to the right. ME is after MA, so I need to go to the left, and there you go, right? And now you see why it's logarithmic, because basically what you learn in computer science is that the depth of that tree, the number of levels to go from up down, is logarithmic in the total size of the tree. And the trick is we don't even touch the rest. Everything that doesn't have a rectangle highlighted around them, we don't even touch. I only touched 4 of the titles in order to find mathematical logic. That is extremely powerful, right? Who has now an intuition of, awesome, perfect. So this is logarithmic. So O of n would be linear, that's the full scan. O of log n is logarithmic, this is what happens here. And there is a third one that is super easy, it's O of 1. O of 1 is magic. O of 1 means, oh, my database has 100 records, takes me 1 second. My database has now 10 times as many records, 1,000, still take 1 second. My database now has 1 million records, still takes 1 second. My database has 1 trillion records, still takes 1 second. That's called constant complexity. Here, it doesn't even depend on the size of your data. It's always instant. And so as a little cliffhanger for next week, it is possible to do that, the same lookup, in a constant time, even better than logarithmic, in O of 1, meaning you can have 1 trillion records, instantly I will find it, right? Instantly. This is incredible, and it is possible. And I will show you next week how you can actually do that. It's called with hash indices. This is a tree index, as we will see next week. Okay. We have just built an index, and this is what we will follow up with next week. Okay, so let me see. Of course, it's going to ask me to refresh again. There we go. We are 24th. Does anybody have any questions before we leave? All right. You know, you can always ask questions, right? You can go to the Moodle forum to ask questions. You can ask your TAs. You can ask me. You can also send me an email. If anything is not clear, I can also re-explain something in the lecture. For example, one of your colleagues asked for the decomposition exercise of the quiz. I will try to explain it to you next week, right? It's always possible, right? So we are here to learn. I'm basically trying to push you a little bit, right? Because I know you're not computer scientists, and this is technically computer science. I'm obviously not teaching you everything that we teach in the bachelor's level, but I'm just trying to push you as far as I manage in such a way that you can still follow, right? Okay, so I still have a majority above 80%, right? And again, don't worry if you're below 80%, just ask us, right? Ask us, read the books, practice with SQL. This is really, really the best way to learn. Thank you very much, everybody. Have a great exercise session. Don't forget to submit the quiz if you want. That's your 3rd chance. And I'll see you next week at 10 a.m. for the continuation of indices. Thank you.